If you double your distance from Earth, you might wonder that gravity just gets cut into half, right? But that's not actually quite true. The gravity gets dropped by staggering 75%. Crazy, right? But why the drop off is so brutal? Now we all know that gravity gets weaker the further you move away from an object. But it's not like gravity has an expiration date or that it simply gets tired and stops working. But the reason gravity weakens with distance isn't a mechanical failure. It's actually a consequence of a pure geometry. Okay, now to understand this, look at a light bulb. If you stand right next to it, the light is incredibly bright. But as you walk away, the bulb doesn't actually emit less light. Instead, the photons are spreading out uniformly in every direction to fill a three-dimensional space. The exact same amount of light is now spread across a much larger surface area, making it look dimmer to your eyes. And gravity works exactly like that light. A planet or star doesn't radiate less gravity as you move away. Its gravitational pull is simply being diluted across a larger canvas of space. Let's take another example. Think of it like a spray paint. If you hold a spray right next to a piece of paper, you get a concentrated, intense blast of paint in a tiny spot, right? But if you back up, the exact same amount of paint spreads out to cover a massive area, making the layer incredibly thin. Which simply means that distance doesn't destroy gravity. Distance just gives gravity more room to spread out. Now let's understand this mathematically. Now this brings us to Newton's inverse square law, which is nothing but the force of gravity is equals to gravitational constant times the mass 1 and mass 2 divided by r square. Now, if we strip away the constants and focus purely on how distance changes the force, then we will get this relationship, which is nothing but force is inversely proportional to square of the distance. Now you might wonder why specifically r square, because the surface area of a sphere is nothing but 4 pi r square. The surface area scales with the square of the radius. Therefore, the gravity spreading across it must drop at that exact same rate, which is nothing but 1 over r squared. So because of this geometry, the drop off is so brutal. Now let's look at the numbers using our formula. Now let's say if our baseline is 1, baseline distance is 1, then the force would be 1 upon 1 square, which is nothing but 1. Now let's just double the distance from Earth and let's take it as 2, the distance. So the formula will be force is equals to 1 upon 2 square, which is equals to 1 upon 4, which is 1/4 of its strength. Now triple the distance, it will plummet to 1 upon 3 square, which is nothing but it's just 1/9. And just like this, as you keep increasing the distance, the gravitational pull continues to shrink drastically.